the new objects for today are going to be, boy, my memory is long here. We're going to find out. Six of them, since you only got 4 last time. What I want to do is I have 2 things in the program today which are not actually to develop new theory, but to continue just sort of showing you manipulative level things that you might want or need. And what they are first off, oscillators are the same thing as, let's see, what's an oscillator look like here? Do not be confused by the fact that OSC and COS are anagrams. Oscillator is oscillator, and cos tilde is a thing which just takes the cosine of what you're looking at. Actually, if you give the input in cycles, so really it's the cosine of 2 pi times the thing. And phasor is the other thing that you need if you want to make an oscillator and someone has to give you a cosine function. And I'll try to explain that in comprehensible terms later. And when you see that, then you'll actually understand what an oscillator is and does. Then the various conversion things, frequency back and forth to MIDI and RMS back and forth to decibels. These are the things that you really use, at least at the first cut, in order to be able to control pitches and amplitudes in human readable ways. So up until today, all of your amplitudes have looked like 0.1 and stuff like that, which is a perfectly reasonable way to operate, but most people would prefer to use some kind of reasonable amplitude units. So sort of stage 2 in knowing how to do that is knowing the usual psychoacoustic or acoustics measure of amplitudes and frequencies, which are going to be, for frequencies, MIDI, which is not really a unit, but which seems to be the easiest way to describe what that is, and decibels, which you learned about in acoustics. All right, so that's, oh wait, you might want to save it. Yeah, let's save it. All right, so with that in mind, I'm sort of acutely aware that I used about 5 minutes in the very end of the last class to suddenly introduce the line tilde object, so I want to go back over that kind of review-ishly and try to make sure that everyone can use it who wants to use it. There will be more about how to use this thing effectively, that's to say programmatically, that I won't be able to tell you today because I won't have all the gluey objects that you need in order to be able to do that. But I can at least keep at it at the sort of level of pre-planned, here are the breakpoints and here's what I want you to do when kind of level. All right, so the usual patch that we've been operating on, or the usual kind of patch, is make a frequency, multiply it by something to control its amplitude, which until now has always been an oscillator because we didn't have line tilde, but now that we have line tilde, pretty much for the rest of time we're going to be using this or objects derived from it for controlling amplitudes instead of oscillators, which are not usual amplitude controllers really, right? All right, so line tilde does something which at the end of last class I was hurriedly trying to show, but I will just develop that again, probably somewhat differently in order to emphasize it. So what we have here is a nice table with 44,100 elements in it, so that it holds a second of sound at the sample rate that we're operating at. And that way we can do things like, oh, first off, let's look at the oscillator, and you'll see what 440 hertz looks like if you graph a second of it. So you get a button. And you wait a second before you see it, and then you see something that, if I were honest, I would tell you that there aren't actually 440 cycles being graphed here. What's really happening is there aren't 440 pixels in that part of the screen, and so it's graphing some unsampled, incorrectly unsampled version of that waveform. But nonetheless, you get a sense that it just fills this table full of values that rampage between -1 and +1. Which is indeed what the output of an oscillator looks like. If you want to see it well, you have to give this thing some much lower value, and then you'll see a reasonable number of cycles, but on the other hand, when I play it to you, you won't hear anything, right? Because 10 hertz is below the audible frequency range. All right, so we go back to this. times. Now what I wanted to do was graph what line tilde does. So let's turn it on. And then let's graph it. Well, that was kind of stupid. The graph actually falls right on the top of the rectangle that holds it. So if you want to actually see it, maybe I should give this. I don't know how to do this in a good pedagogical way. I could make the table go from -2 to 2, which I've done a couple of times. There. Now you're looking at, yes?
What's the 300 in this?
Okay, yes, I got to get to that. Okay, so the 300 is the amount of time in milliseconds that it takes to attain the value that I gave it as a target. So here, the target is 0 and the time is 300. And that's right. Or from wherever it was to 0, right? Because if it is at 0 and I ask it to do that, then it has to go from 0 to 0, which means it just flatlines. Right? Okay. Or to make it painfully obvious, we'll put a delay on the graphing. On the message, like this. Oh, I didn't do that right, did I? Oh, I didn't tell it how much to delay, did I? Okay. So we'll delay another, I don't know, 400 milliseconds. I'm going to turn it off. And then, there it is. So this is what, oh, now I'm turning it off this way. All right. So this is what line tilde does. It starts wherever it was, and when you send it a message, so the message 0.95 space 300 arrived at this point in time because I started graphing 400 milliseconds earlier than I sent that message, and line tilde's way of responding to that message is to ramp up to its target value, which is almost 1, and do that in the next 300 milliseconds. So it doesn't look like it, but this should be 4/10 of it, and this should be 3/10 of it. Something bothers me because that really doesn't look that way to me right now, but maybe it is. Yeah, I'm looking at it from real close too, so who knows. All right, or conversely, and sorry to insult your intelligence, but we'll do the same thing to get back down. Oh, with a different message, with a different button. And now, of course, if I do this, nothing happens because I stopped the SP, sorry. Oh, this is going to be very confusing. The delay sent the message anyway, and then this thing happened, and that all happened while DSP wasn't running, so they all took effect at the same moment. So that wasn't what I wanted to show you. I want to show you this. There's going up, and here's what it looks like to go down. Oh, and here's what it looks like to go up and down. And pretty soon, you will be building synthesizers. Whoops. What did I just do? I want to make this a little smaller delay. Turn it off. No, I'm sorry. Turn it off and then do this. Oh, man. Let's do this for real. What we're going to do is we're going to turn it on after 100 milliseconds, and then we're going to turn it off after another 400. Ah, there it is. All right. Now, someone who doesn't understand this, ask a question. Or you just need to stare at it. That's a possibility too. Or is this just clear? Probably not. Okay. What's not clear about it, first off, is that you can't actually see from a patch what objects are doing the good thing right now and what aren't. That's a problem which no one will ever be able to solve. But what happened was you can pretend these things aren't here because they're not happening right now. Let's actually cut this. Actually, let's just blow the whole thing off. We don't need it. So now what we have is, oops, okay, so I'm going to save this, because this is a good moment. So what happened is I hit the button, 100 milliseconds later, a message comes out of this delay, a bang message comes out of this delay, and it does this, which means over the next 300 milliseconds we're going up. Then, how long does it stay at 0.95? 100. The remaining 100 milliseconds between this 300 and this 400, because another 400 milliseconds later, this message gets sent. Well, delay sends a bang, which causes this message box to send the message 0300 to the same line tilde, which therefore goes down. And the whole thing fit within a second, so we got to see it all. Yeah?
Everything makes sense, except for, can you just kind of go over exactly what line tilde is doing again? What's the function of it?
Yeah. Okay, so
what did it replace? You said we used before.
oh, but okay, so there were examples earlier where we did things like this. Let me break this for a second and do this. OS oscillator, a couple of hertz, multiply by that, right? And that's an amplitude control. This, whoops, hey, go away. This is another amplitude control, but it is an amplitude control that lets you tell it what you want it to do, really, as opposed to just sitting there and doing something by itself. So answer number one is oscillator tilde could be used as an audio generator or as a level control by using it to multiply by another oscillator or something else. Line tilde also could be used as a straight signal and you would hear a thump, or you can use it as a level control by multiplying it by something that you want to hear. Line tilde makes this kind of waveform as in contrast to OSC tilde, which makes this kind of waveform. If I can graph this. Now I need another button that does just the graphing. So there's what the oscillator does. So oscillators make sinusoids. Line tilde makes line segments.
You said something about you can't use line or the line tilde as a signal and it sound like a thump.
Yeah, maybe I shouldn't have said that. If you want a kick drum sound, make one of these. Sorry, not what you just heard, but make one of what you just saw. I shouldn't be telling you this. This is not good computer music here. But you can listen to the line tilde object, right? And if I do this, you won't hear a thing, and maybe you'll see the speaker cone move a little bit, maybe not even. But if you do this real fast, like if I replace these numbers by tiny numbers like this, let's replace this by 4, and make all these numbers, a couple. Then I've got a nice sound that does that. That's this. Oh, there it is. That's the sound of a pulse. What I did was, you can't really see it in detail, but that's a ramp that's going up in 2 milliseconds, and then it's staying up at the top in 2 milliseconds, and it's going back down. 6 milliseconds wide, which means that the bandwidth of it is, well, never mind. It's audible. It happens fast enough that you can hear it. The first number, yeah, is the, okay, this point 0.95 is the height here, which is the, yeah, amplitude is one of those terms that can mean anything, but, I mean, amplitude just means how big it is in some sense. So, yes, it's the amplitude. Like this. All right? Anyone want to predict what that will sound like? Yeah. Looks different, but sounds the same. By the way, there's no reason that your ears couldn't have been designed in such a way that would sound different. That's a way that you can encode secret information, the signal that no one can hear. You've got the sign as a completely inaudible but very present parameter. Okay, so there was that. Yeah. Okay, let's go back to reality here. Okay. So anyway. let me go back to real reality, which is I'm going to go back to using this as an envelope in some kind of reasonable way. And yeah, okay. Now you didn't hear this because I just played the output of the line tilde, not the thing that was having its amplitude controlled by that. But you can imagine that if you took a sinusoid and multiplied it by a signal that started at 0 and then gradually went up to 1-ish and then went back down to 0, that you would hear the sinusoid turn on and off. And further, and that's what you heard before, which is this sound. And furthermore, it might be helpful, let's get rid of this. Furthermore, it might be helpful to graph that. Oh, the array is going from -1 to 1, and it's 44,100 points, which means 1 second. And I have it graphing points and not lines, I think. Although it doesn't look like I'm doing that right, so maybe that's not true. One little thing about that, there's another good thing in the properties of an array, which is that you can select whether you want it to, where is it? Here. You can, there. There's some place where you select whether you want it to save its contents. Sorry, I can't find it now. Maybe it's gone. Am I going nuts? Oh, save content. Here it is. If you uncheck that, then it will not pollute your patch with 44,100 values of whatever is sitting in the array. And then when you load the patch, it'll be zeros, and your patch will be many, many lines smaller, which might be a good thing as soon as you start putting large values in the arrays. Yeah?
Just like on Max, how do you get the array
On
Max?
a Macintosh, how do you drag the... Yeah, you have the test version from December, or maybe. Really? Maybe you still can. Ooh, okay. This sounds eerily familiar, but I thought this problem had gone away. I've seen this. I saw this last year, but so I should go back to worrying about that. I suspect that there might be weirdnesses for like OS 10.4 if you have an old one, but no, otherwise, because I heard some reports about that. So I don't know. Maybe I should look at it later. I mean, I know what it'll look like because I think I've seen it, but it's odd that it's still happening. Is everyone else getting? Yeah. So on a Mac, when you do this and get the properties, do you have a way of moving the properties out of the way? Because no, that's not good. I've had it on Macintosh. It's sometimes happened that you get these two dialogues show up, and the array properties are right behind the canvas properties, and furthermore, you don't get the area that allows you to drag the window so that you can't move it. You can. Okay. You can't. Okay. So it's 50-50 whether you can move it or not. Okay. Okay, I better go looking at this. All right. Okay, so what you're looking at now is not the output of the line tilde, but the result of multiplying it by the oscillator. So you've seen what the oscillator's output looks like. It's got a constant amplitude of 1, and it's batting up and down rapidly. Now what we have is nothing, because no matter what's coming out of here, you're multiplying it by 0, you're getting 0. And that's nothing for the first 100 milliseconds until the thing ramps up. And then there's a period of 100 milliseconds. It's not too clear where the thing is flat. And then there's a period of 300 milliseconds when it's going to down. And this is what the output of a well-formed computer music style instrument should look like. It should turn on in a gentle way. Well, at least it shouldn't turn on by just turning on, and then it should not turn off just by turning off either. So bad computer music style might be to do something like this. Actually, I'll just simulate it. Suppose I either didn't put the line in and just put the thing right in the multiplier like this. Yeah, I'll do it this way. So I'm trying to figure out how not to be confusing. Yeah, maybe the least confusing thing is I'll put times of 0 in here. Now we have a computer music instrument that goes, that makes a pop when it turns on and off. Okay, always differently to boot. And what you see is that every time I whack it, I get something somewhat different. It jumps from 0 to some value, whose value depends on what phase the oscillator happened to be at the moment when I clicked the button. Or actually at the moment when the computer decided I had clicked the button. Right? And so that particular time you didn't get a huge click because the value was relatively close to 0 right when I whacked it, but if I whack it again, that one it really was very smooth on, but it was not smooth off. And you just get what you get. There it was bad. It jumped almost to full blast right at the outset. Okay, this is a good way to make annoying sounds. As a rule of thumb, let's see, this is either a function of psychoacoustics or a function of personal preference, depending on your philosophy. If you give this thing at least 5 milliseconds to go up and down, you will get something that most people don't perceive as having a click at the beginning and end. And that, in my opinion, is about as fast an attack as you should have on something if you don't want to have a snapping sound at the beginning, a click. Right? Unfortunately, that number is not a constant of nature. That number depends on the frequency of the oscillator. The low frequency tones, like 50 hertz-ish, you will still hear a ugly popping sound even at this speed, and you will have to make this number larger. So then it's a question, how do people who play bass play their instruments? It doesn't take 20 milliseconds for a bass to start sounding, and so there isn't a ramp of 20 milliseconds, and yet a bass, when you pluck a string, doesn't click. There's a reason for that, but I'll try to explain that later on. It is possible to make things that go on quickly without clicking, even if they have bass frequencies, but you will have to be smarter than I taught you how to be so far in order to pull that one off. In particular, you should make it so that the phase of the oscillator is something appropriate for quickly starting up when it starts. So we have sort of barely acceptable computer music instrument here, and while we're doing computer music, let's make this delay be just the rise time, which is 5, and let's make this delay be a half second. And now we have the standard computer music bell. All right? This is incorrect, by the way. There is no bell that decays linearly. What would be the correct decay shape for a bell? Yeah, well, logarithmic is, that's one way to say it. It should be a falling exponential, which is to say, if you took the logarithm of it, you should see a straight line going down. It's an amazing fact that a mass and spring system, like the ones you studied in Music 170, as they decay, they lose a fixed number of decibels per second, so that if you believe in decibels as a psychoacoustic measure, the rate of drop-off is actually constant as you listen to it, which is why bells work as musical instruments in some sense. This doesn't work. It sort of hangs in the air and then ends in this sort of, I don't know what. That doesn't sound right. It sounds like it was ringing for a while and then someone damped it, as opposed to someone let it ring for the amount of time it should have been. And if I graphed the logarithm of this, which would be how you heard it, in other words, if I graphed it in decibels, well, I shouldn't take the log of this, but I could take the log of this. This is now I'm just showing you the input generator again. If I took the logarithm of this, you would see something that started off not quite level, but then suddenly started dropping precipitously later on in the show. Until finally here it hits minus infinity because the logarithm of 0 is diverges. Questions about what I've just put down? I'll probably say this again and again in many different ways. Yep.
So how would you change the line?
Yeah, how would you make it be logarithmic? Oh, that's a good one. I intend to bend your ears very seriously about that in the coming weeks. There are 5 or 6 ways you could do it, depending on the exact spin that you want to try. One thing that you could do is you could say, oh, you know what? I'd have to introduce an object that I've not really introduced yet. So let me go on to units, because once I've talked a bit more about the psychoacoustic units, then I can answer questions like that a bit better. Other questions? Yeah.
Maybe backtrack a little bit. You said 500 milliseconds is half a second.
Yeah.
What would the 44100
Ooh, that is a good question. Okay, units in PD are confusing. 44,100 is the number of samples in a second. 500 is the number of milliseconds in a half second. And sometimes in PD land, time is in samples, and sometimes time is in milliseconds. This is just kind of unfortunate. I don't know any way around this situation. PD doesn't actually believe that the axis here is time. This is really just an array of numbers, which of course you could treat as an audio sample, which is the way I'm treating it right now, but it could be probabilities, or it could be weather data, or anything, right? If you want to use this to store a sound, the natural thing to do is have the horizontal axis be samples, of which each one is 1/nth of a second, where n is the sample rate. And that number varies. If that number were just always the same, then things would be a lot easier. But in fact, well, you know, sample rates vary depending on what you're trying to do. If you want to find out about dolphin songs, you should not operate at 44K1. You should operate at a couple of 100,000 at least. So that explains the value of 44,100, which was the size of this array, which we set in the panel where you set the size of the array. Here, these are values of time, which are of interest to line tilde. So another part of the answer to that question is different objects, for instance, line tilde or OSC tilde, take their inputs to mean different things depending on their functions. So OSC tilde, its input is setting the frequency of that object, and line tilde, it's when I'm sending it messages like this, the message is interpreted as this is an output value, which itself is in arbitrary units, which matters to the next object down. And the second thing is a time, which is in milliseconds, and that is possible because line tilde is the thing which actually runs in time. And so it has access to what the real value of time is, so it can operate on a time unit as opposed to a unit of samples, which is unitless really. Is that something like an explanation? Okay. So in general, yeah.
So you can use line to set the
Yeah. That's a fun idea. You can use line tilde to set the frequency of an oscillator. And the answer is yes, you can. And why not? Now, these are not good frequencies for an oscillator, right? So, I don't know, 440, and let's make it a half second, I don't know. Whoops. All right. So now we'll turn it on. Hello, let's see. I don't hear anything right now. Oh, yeah, of course. All right. Now, now we've got full computer music, right? Because, well, never mind that comment. So you can hook anything to anything. The only restrictions being that that there's a distinction of type, which is to say something can be a number, which is happening at the time of messages, or something can be an audio signal, which is something that comes out of a tilde object, and basically, well, yeah.
Is the line up there for the, does that have to, could that be a message line? Is there a version of message line, or is it a signal?
There is. You could do this. Watch this connection when I change that. Doing it turned into messages, and now you'll get a wonderful effect. I'm not sure you'll hear it, but we'll try. Oh, it's too good. Let's make that a smaller number. Oh, that's too small. Oh, you almost can hear it now. Hear an arpeggio? The reason it's arpeggiating like that, and I'll make it more, I'll put it more in your face. The reason you hear those values in the middle, this thing, which I wasn't going to tell you about, is a version of line tilde which puts out messages at a fixed rate. What rate? The rate that defaults to 20 milliseconds. Why 20 milliseconds? Because people used to use this to control MIDI devices, and if you try to ram more than 50 messages down a MIDI device line, you can get into trouble for various reasons. So this exists, and anyway, sending a message to OSC tilde changes its frequency just fine, but it changes it in a way that happens right when the thing happens, as opposed to doing it continuously the way a signal would. Another way of seeing that is our old friend print. So first off, there's nothing coming out of line. But if I tell it to ramp up to 880, oh, whoops, it was at 880. That wasn't a good example. I'll ramp it back down. And it says, oh, okay, 20 milliseconds later, we'll go here and here. And this is the arpeggio that you heard, which was too fast to really hear very well. Okay. So, yeah, so now you have that, or you've got, I'll disconnect this because it doesn't make sense. The version I showed you before, which is the smooth one. Okay. Was that clear to everyone? All right. Yeah. Yeah, it makes it into an audio signal, which, for practical purposes, is continuous. Yeah. In fact, I think I've been using the word continuous, but now that I hear you use it, it's a bit of a lie because it's really just continuously at the sample rate. Yeah. Oh, yeah, and we can do that here too. And this is going to be rotten. Let's do 100 here. I don't hear anything wrong. We don't have, if you listen to this over headphones, you wouldn't like it. Can't hear it in this room, I don't think. Or at least I can't. What you should hear is a gritty sound that's called zipper noise, which is the effect of this thing. So there are 5 steps going from 0 to 0.95, and this thing is changing discontinuously, which is therefore a click, like this. Let's see. So here's the crude way to turn things on and off. Okay, so if you do it this way, you have the same thing, but each of the jumps is only a fifth as large, so they're a great deal quieter and they're buried in the sound of the oscillator. But if you do that over headphones, you will hear something bad. It's easy to track problems down when things are really bad, but when things are only just a little bad like that, then you will have to listen to your thing very much more carefully and more critically in order to be able to find the problem. better if you can to avoid getting into that situation. So that's line as opposed to line tilde, which will do it correctly. Yeah.
So the message at the top is every 10th of a second. After you click it, it takes a 10th of a second to go to 110. Is that right?
Oh, let me see. Okay. So you're referring to this network over here. So let me. No, these two. Okay. So let me. So what's happening here is, right. Okay. So in a tenth of, whenever I whack it in a tenth of a second, it goes to it. Over the next tenth of a second, when I whack it, it ramps from wherever it is up to the value, or down to the value of 880.
So assuming you just set this up and then you turn on DSP, what's the starting value before you
0. Right. So now, for instance, if I'm playing the sound and I say, okay, give me a new one of these, it's putting out zeros until I decide to send it a message to tell it to do something else. Now that we've done that, do you remember that I showed you how to do rudimentary frequency modulation? This is this isn't exactly an aside, this is an embellishment. Right? So now we're going to do save as, and we're going to say 3 FM again. And now, let's see, let's get rid of I don't need this anymore. This is gravy on the cake. But what I need is now to have an oscillator whose frequency is, I'm going to recreate it as much like the old value as the old one as I can remember. So I'm going to add 440 to another oscillator in order to create this oscillator. And that other oscillator is going to be an oscillator with an amplitude control. So let's get these two things out. Ooh, these three things out. So this is an amplitude-controlled oscillator. That's all you really need to do it. So here now, if I listen to that, like this, I get, whoops, I don't have the off button. Sorry. Okay, there's that. Now I'm going to take that, and instead of sending it up to an amplitude of 1-ish, I'm going to send it up to an amplitude of 1,000-ish. Okay, do not play this through your speaker. And meanwhile, I'm going to make it slower so that you can hear what's happening. And what I'm going to do to this is I'm going to add 440 to it and make it be the frequency of another oscillator. Let's just make sure this is off. And I'm going to clean it up a little bit so that you can see it better what's going on. All right, oscillator. Okay, now what we're listening to is this oscillator, and right now it's playing at 440 hertz. And this is going to apply vibrato to it. The vibrato is going to be at the audio frequency also of 440 hertz. And it's going to have amplitude of 0 up to 1,000. Okay, and that's the sound that I incorrectly said was 60s computer music. This was invented or published in 1973, so this is 70s computer music and not 60s computer music. That's a correction from last week. My apologies to John Chowning, if he ever sees this video. Oh, John Chowning is the originator of the frequency modulation technique, as we all know, and anyone who has a cell phone uses FM all day long. For which I once heard John say he was sorry. All right. Okay. Now this is an excellent moment to ask if people understand what's going on or not. Let me tell you one useful thing. Sorry? The graph parameter. Okay, I didn't actually graph anything just now, but the graph parameters are properties. It's got a name. It's got 44,100 And I'm saving contents, which I probably shouldn't, and it's polygon despite the fact that I don't have the big points. And, oh, whoops, I closed the other thing too. And then the canvas, that's to say the graph that it's in, is the range is, the X range is set, the horizontal range is set so that it holds the array. You can change that, but, well, oh, okay, so arrays actually are indexed starting with 0, C style, so really the graph could have been from 0 to 44,099, but what would that change? That might move one thing over one pixel. Also, I mean, you can also lie to it. I mean, you could say, I want you to start graphing 1,000, please. I think I already showed you this. And then it's all very good, except that the thing is, oh, where did it go? Oh, I just destroyed it. What did I just do? All right. Can't see it anymore. Sorry, I didn't want that array anyway. What was that all about? Okay. Never mind. All right. Anyway, there you have it. So, what's happening here is, first off, this thing is repeating every, I don't know how to describe this. Okay, this is an oscillator nominally which is operating at 440 hertz. And I'm applying vibrato, but the vibrato itself is repeating every 440 hertz. What that means is that rather than changing the heard pitch of the thing, I'm changing the pitch so fast that it's actually changing the waveform. Or to put it another way, the result is repeating still every 440th of a second. The thing is repeating at 440 hertz still, even though its pitch nominally is changing. It's happening within a cycle, and the cycle is always the same period. So we don't hear any change in pitch when we start applying vibrato. Let's do a couple thousand. So if we're not changing the amplitude and we're not changing the pitch, then the old psychoacoustics joke is that if something isn't amplitude and it isn't pitch, it must be timbre. So we're making a timbral variation on the sound. And there are ways of describing mathematically what's happening here, which I won't go into, but I will go so far as to graph these waveforms so that you can see the vibrato in action. That's a good thing. And to do that, I have to now change the parameters of the table. Whoa, that was the wrong button. Properties. Okay, so let's have the thing only be 1,000 points now. So now I'll, let's see, let's graph just the output of the oscillator without worrying about the amplitude. And it won't do it because I have to do something else. Now, this is the old 43 test plug. Yeah, question? This. It does, yeah. So the first oscillator, oh yeah, so if thinking of it that way, the first oscillator is at 2,000 volts right now. Right? It's actually varying between plus and minus 2,000 volts, and then I'm adding an offset to that, so it's varying between 2,440 and minus 1,000 something. That would be, yeah.
Sorry, could you explain the first number of 2,000?
Okay, this is going to be the target value that line tilde gets. So if I graph the line tilde output, it would be 2,000 units north. Right?
I understand that as
Oh, what unit is it? It's in whatever units the thing that I put it to is taking it to be. In other words, it's really just a pure number. And the units only become relevant when you use it for something which is down here. So it's just sort of knowledge about the patch that this is all operating in hertz. And the reason it's operating in hertz is because this oscillator wants the thing in hertz, or cycles per second. Yeah.
The 2000 is more like amplitude, because you're not connecting them directly to the oscillator.
That's right, and that's why amplitude is such a slippery word.
Right.
It's both an amplitude. It's an amplitude, but it's an amplitude that is in hertz.
Magnitude.
Magnitude, but magnitude means, yeah. This is a question. I think of amplitudes as being able to be positive and negative, and magnitudes as being the absolute value of the amplitude. That might be local usage of mine. It's the usage that's in my book if you go looking for it. It's also what the quantum mechanician would say, I think.
If that's 2000 hertz, then it's not oscillating at 440. You are changing pitch.
That's right.
Yeah, 440.
And yet, yeah, and yet the change that I'm making in the frequency of the oscillator is varying, but it's varying in such a way that all adds up to no variation, because there's as much positive as there is negative in the sinusoid. It's, so half the cycle here, this thing is adding to the frequency, and the other half the cycle is taking away from the frequency, and so the average frequency is still 440, even though it's going up to much higher than that and down to something negative. Yeah, it's hard. Let me see if I can graph it. It might make it a little clearer. Okay, let me graph it. Hang on to your questions for just a second. Where did I go? Oh yeah, I was going to be sane here. Let me change it to 2 and -2 again. I still can't get my head around your question, but
No worries.
but that probably means it's an interesting question once I manage to figure it out. Okay, so now we're looking at the oscillator, but we're not changing the frequency. So now you see the period of the oscillator is from, for instance, here to here. It's about 2/5 of this window long, right? Okay, I changed the window, by the way, so that it's, I think, 250 points now. So it's a very short amount of time in the life of this sound. Now I'm going to send the oscillator up to amplitude 2000. I'm not going to graph that because it would be through the roof. Right? But you can now still look at the output of this oscillator, and then you get, okay, now this requires some explanation. It still has the same cycle, but you know what, let me, before I give it 2000, let me give it some smaller number like 440. No, smaller than that. Okay, here, this is easier to understand now. Okay, so you see still the cycle. It's still cycling from here to here, but it's going too fast, and then after that it's going too slow. Okay, it's going faster here because at this moment in the cycle, this oscillator was positive and therefore was adding to the frequency. So it sped up to some frequency much higher than 440 hertz. But then over this period of time, it has slowed down to some frequency much lower than 440 hertz. And on average, over the cycle, the frequency was 440, and so it actually made it through the cycle in the correct amount of time. But it did it in a non-uniform way, whose result, therefore, was not at all a sinusoid. And then if you listen to it, you won't hear a sinusoid, you'll hear some other waveform that has some other partials. Because waveforms have partials. Okay, now what was your question?
Ask this, but considering you have bipolar, it was negative,
Uh-huh.
but if you make it like unipolar, you would almost have it. So you only have magnitude. You know what I'm saying? So like the lowest would be 0 as opposed to being
Oh.
fluctuating between positive and negative.
So, yeah, there are a couple ways you could do that. You could take the absolute value of it, which would mean that negative values would simply be negated so that they became positive. Or you could slide the whole thing up by adding 1 to it. Okay. And then you would just see the entire waveform do that. Oh, that would be if you added 1 to this oscillator. This oscillator right now has an amplitude of 330, but I'm adding 440 to it. So if I graphed it, I would see it would all be positive. In fact, it's all ranging from 110 to 770.
And they're falling magnitudes.
Yeah, I mean, in my way of using amplitude and magnitude, I would say that magnitude is the amplitude because the number is a positive real number whose absolute value is itself, but I wouldn't ever say something like that except to confuse someone. Goal achieved. Right. So these are amplitudes which are variously positive and negative, but if you added enough to a sinusoid, if you added enough of a constant to a sinusoid, it would all be positive, and then its amplitude would just be positive. Oh boy, you always have phase issues, but they would be different phase issues, yeah. But that probably didn't answer your question very well, did it?
As much as I want to get.
I think the gist of it is you're confusing yourself by using the word magnitude. Or
make it bipolar? Or I'm sorry, unipolar?
Right. And you just be dealing with magnitude.
Yeah, you could.
but how would that help you?
Yeah.
It's the same thing with shift left.
I mean, sometimes it is, sometimes it does not fit together.
Yeah. I mean, I could do that to this, and it would, and then the frequencies wouldn't. That's the right way of saying that. I'm scared you to do it. The result would be complicated. Yeah. Okay.
I'm not like a ball.
So, okay. So now if I make this value bigger, let's try 1,000.
So then after that value, you get specify a time for it, or the default is
0. That just means do it right now, please. Yeah. Oh, so this is equivalent to 1,000 space 0. And now we have the following hilarious sinusoid, which did get around to phase 0 once in a cycle, but in fact was going. You can't see it right now. I'm going to just scramble the phase a little bit and see if I can get a better one. Oh, there we go. All right, so at some point it hits 0 phase, and then it goes racing along until at some point it decides, yeah, I went a little too far, let's go backward. And so I think at this portion of the waveform, the thing has actually got a negative frequency and it's going backwards until it decides it's gone backward enough and then it rushes forward at superior speed. So by pushing the, okay, so what I did was I made this oscillator have amplitude 1,000, which therefore is so great that it even after you add 440, it has both positive and negative values. And therefore you see the thing wrapping both forward and backward during the cycle. Yeah. In fact, you can do more of it. So now I'm going to ramp it up to 5,000 and then graph it. 2,000, sorry, yeah. Oh, all right, let's make it 5,000. Ooh, and there, maybe I shouldn't be graphing points after all. All right, let's go back to graphing the stupid, way with polygons. Polygons are better if you have smaller numbers of points. There we go. This is the classical pedagogical waveform that you show when you show frequency modulation, which is the thing is wrapping forward crazily and then wrapping backward crazily. To add up to just one cycle forward. Yeah.
So that would just show that the 5,000 is the line
Okay, it's the output of this oscillator, and the oscillator's frequency is averaging 440, but it's varying by 5,000 around that average, which means it's It's rarely in the vicinity of 440 anymore. It's just being scattered all over the place.
If there's that for the price for the value, the is that just the initial
Oh, this is getting added to this oscillator. Oh, you mean this 440 on top? Oh, that's a good question. What if I make this 440 something different? Let's turn it off first. So, okay, so now we're listening to the same thing, and now we'll turn the. So now what we have is something that looks like this. What I did was I made there's the original tone, which is an octave higher. Now what I'm doing is I'm varying the frequency at a rate so that it evens out only over 2 cycles. So the resulting period is in fact 220 and not, sorry, 1/220th and not 1/440th. So this is the frequency at which this thing is changing. Now the variations are taking twice as long to cycle. But this is still the center frequency, which could be some other number if you wanted to. Yeah. Right. The line controls how widely it's varying around the center value of 440. Is how quickly the variations happen. Right. Yeah, that's it. So the frequency of this oscillator is 440 with disturbances. The disturbances have both an amplitude and they have and it has a speed. So the speed is 220 times a second, and the size of the disturbance is 5,000 or whatever it is that I set it to.
And that's 5,000 hertz.
Yeah, because it's being used as hertz because oscillator is these magnitudes are eventually finding their way down here, and then they're being used as hertz. But I could use this to read a sample or something like that, and then it would be giving us something different. Yeah. Well, it is FM modulation. It's frequency modulation, which is FM. You could even think of it as being overdriving something too, but I'm not sure what. Maybe, yeah. I'll talk more about wave shaping and overdriving stuff later on. But it is a sort of overdrive. Now, okay, so gravy on the cake is, why don't we just make this thing be something we can control, like this. Now I'll go back to the original. So now the amplitude now is 1,000, and now I'll start changing this frequency continuously. So this now looks like this, and you don't see a period. In fact, you have to wait an entire second, I think, before. No, you have to wait a fifth of a second before the thing all wraps around. And so now you get something which is a nice inharmonic tone, and you can analyze this and find out what the frequencies of the inharmonic partials are, which I think we'll manage to get into week 6 or 7. But here I'm just showing that this is a thing that you can do. And of course, the amplitude can still be varied. The amplitude of the vibrato oscillator, sorry, the amplitude of the modulating oscillator can be varied, and then you get those good 1970s computer music sounds. Yeah.
Just quick, this is
Oh yeah, okay. All right, speed it up. Now this is going to sound bad with these values, but we'll do it anyway. Well, okay. Well, okay. I guess you could like that. What I don't like about it is that you hear this sort of wah-wah effect as it's changing index, and you can't get that wah-wah effect out. And it's cool for the first 5 minutes, but then you get really tired of it, and you can't iron it out. You have to just turn to a different synthesis method at that point. Most people who use FM don't use these kinds of values. They're good pedagogically because there's no possible way you can miss hearing it. But if you keep these values on the order of this, or maybe even twice as much as this, you don't get that wah-wah, but you still get a timbre variation. But you don't get a whole lot of high partials. So then if you want high partials, but not the wah-wah, then you have to think a little harder. Yeah, there are 5 or 6 ways I could tell you to proceed. But that happens later. Other questions about this? There's a homework assignment for next time, which is on the website, but I haven't made the WebCT upload hoo-ha yet. And the homework assignment is actually not to do FM, but is something that you will need line tilde for, which is to make a collection of 4 oscillators that makes a tone that breaks up into 2 tones after you've enjoyed it for a while. So it's, let's see if I can actually find it. Okay, so we're going to be me, and we're going to say courses. Now, the gotcha is I don't think I'm going to be able to get my computer to play this. This is a graph that shows you how you could do the thing, which you will not be able to hear because I haven't configured. Oh, maybe it'll. Yeah, right. It's playing it out some other audio device that I don't know how to control. So forget that. You'll hear it as you play it. It'll start out as a nice tone. Oh, so this is a time versus frequency plot, which is a way of describing how you might wish the partials of a sound, which are these sinusoidal components you add up to make a sound if you believe sounds are made up of sinusoids, which they could be. So, and what I'm describing here is how the frequencies of a bunch of sinusoidal components might change in time. If you played this, and for instance, the amplitudes are not shown here, but if you made the amplitudes all equal, which would be a good idea, when you play these 4, you will hear a tone. At least if the 4 sinusoids start at the same time, you'll hear a tone, whose frequency will be that of the fundamental, which I think I suggested might want to be 220 hertz. And so if that were true, this would be 220, 440, 660, 880. And you would hear a nice tone until this thing happened, at which point a wonderful psychoacoustic effect would take place, which is your ear would quit being able to hear this as a tone. You would still hear this and this being fused as a single tone at this frequency, although its timbre would change because it would no longer enjoy even harmonics anymore. And meanwhile, you would hear these two. Oh, what's the interval between this partial and that partial? The interval 2 to 1 is the ratio. Yeah, so an interval is a ratio, really. So the interval of 2 to 1 is called an octave in music land. So since these are an octave apart, they in fact could also function as a tone at this frequency that has 2 partials. And you will hear that tone as soon as this thing starts sliding away, because your ear will no longer allow it to hide behind these partials to be considered part of this tone. So what you'll hear is a single tone that bifurcates into 2 tones, paradoxically. One of them consisting only of odd harmonics, harmonics number 1 and 3, and the other consisting of harmonics 1 and 2 of a different pitch. And that's a wonderful thing to contemplate. I didn't bring it along this time, but next time I'll play you some music by Jean-Claude Risset, which uses that in interesting ways. Basically, you can design timbres that you can tear apart and make a series of pitches out of, or collections of pitches out of. It's fascinating. And And it is indeed 60s computer music, because that was stuff that they did before they even had access to frequency modulation. So this has nothing to do with FM. You can do this just with additive synthesis is what computer musicians say when they're talking about making a bunch of oscillators and adding their results. So you can make this by adding 4 oscillators up, and now that you know about line tilde, you can arrange for the frequencies of oscillators to slide from value to value. And of course, you should make the whole thing be turn on in a smooth way, and then do this and then turn off. And that will require also that you have delay objects, because you want the ramp up to start here, but then you want the change in frequency to start here, and then you want to ramp down to start maybe here.
Basically, probably just using delay and line to, I mean,
yeah.
an oscillator.
An oscillator is, yeah. It's basically just practice with the objects that you all know about. Yeah. Oh, how would you ramp the thing down? Yeah, you can't show it. I'm not graphing amplitudes here, but frequencies, so I would have to make a separate graph to show how the amplitudes would change. And yeah, just have the line tilde multiplied by the whole rec. And then after an appropriate delay, you send that a nice message 0 with a time value. And then it will turn off. And then when you do that, you will have full access to all of additive synthesis. At that point, you can make complicated, well, okay, your patches will be horrible if you actually try to do it without introducing some automation, but you will, at least in principle, have control over the detail, over the structure of the harmonics or inharmonic partials of any sound that you want to make, which could be powerful.